Good afternoon, good evening, everyone. Welcome to week 6 of the PMRF NPTEL course on signals and systems. Myself, Shouharda Ghosh, a second year PhD scholar in the Department of Electrical Engineering at IIT Gandhinagar, and this is the Monday session for the Signals and System course. In week 6, we have the following topics. The first one is the continuous time convolution integral, which is the key ingredient for any LTI system, the convolution integral, we shall see soon. Then we have certain properties of LTI system like commutative behavior, distributive behavior, and associative behavior. Then we have the memorylessness, or the opposite, which is the memory property, as well as the invertibility. Then we have also covered causality and stability for the LTI systems. Okay, so before we jump into problem solving, let us briefly look into the convolution integral. So as mentioned earlier, from a signal and system perspective in electrical engineering, we have the input signal xt, which is processed by the system, whose impulse response is denoted by h of t. Note that we are dealing with LTI systems, and that's why you are able to will be able to do the upcoming analysis. Okay, so for LTI systems, we actually write yt is equal to h of t convolved with x of t. Note that this star operator, when I am writing it means convolution operation, and this one, this x symbol, actually means multiplication operation. So these two operations are obviously not the same. Now, how do we define the convolution operation to take place? Okay, so what is this h of t? So the h of t makes sense when you give an input x of t equals delta t, and let me write the application into the system. So anything like this can also be denoted as the transformation of the signal tx of t gives me yt. So what do? The transformation of this xt, or the transformation of delta t, gives me h of t. So whenever I give an impulse, I get an impulse response h of t. Alright, I call this as the impulse response, and this impulse response is helps us determine a lot of the properties of our system. So okay, so if the input to the system is delta t and my output is h of t, then for any general signal xt, what will be yt, and that too it should be in terms of xt and ht. Okay, so let us investigate a bit deeply. So when we have any signal, okay, this is the x of t signal, any arbitrary randomly moving signal. How can we write this signal? Okay, so before writing this signal, let us capture a particular instant, a particular time instant, infinitesimal small instant. Okay, and I denote it by t naught, and the value that I have captured over here is what? It's x of t naught. All right, it's x of t naught. Okay, so in how can I capture this sample? If I take this signal xt and then I multiply it with a impulse located at t naught, which I denoted by delta t minus t naught, I get an impulse which has a value of xt naught at the location t naught. Alright, now if I use now the entire signal can be captured by infinitesimally small length these impulses, so I can multiply these impulses with the signal and get the values of each of them. So what can I write? I can write xt x at some position t naught is what? Xt can be written as xt naught into 1, or can't I write it as minus infinity to infinity x of tau delta tau minus t naught d tau. Look at this very carefully. What am I writing? X of t naught is x of t naught times 1, or can be written as x of t naught times delta tau minus t naught dt, because integral over the Dirac delta function placed anywhere can be 1, and since I'm sampling it at t naught, I will take the impulse at t naught. Now I can easily place this x of t naught inside this delta tau minus t naught, and actually it's going in the reverse way. So the general integral is in the limit sense of is actually the variable will be tau. So you have a tau axis, you have this x of tau, and at a time t naught you are capturing xt naught. So what is this? It's x tau being captured at t naught, isn't it? So let me replace t naught by t, and I can write x of t is minus infinity to infinity x of tau delta tau minus t naught into dt. And we also remember a property that okay, Okay, so when x of t is made up of all these impulses, x of 1, x of 2 and all of these, now when I apply this entire thing to the system which has impulse response h of t, so what will I get? This is an impulse. So let's say the impulse has an amplitude a. So when an impulse has an amplitude a, then this one will be a. This will be what? It will be a h t. Okay, it will be aht. Due to this integral, due to this impulse, I will get this response. So the output will be what? Yt will be transformation of xt. Okay, and this xt can be written as minus infinity to infinity integral x of tau delta t minus tau d tau. Okay, because delta tau minus t and this delta at is 1 upon mod delta t. So delta minus t is okay, fine. So let's ignore all of this stuff. So it will be integral minus infinity to infinity x of tau transformation of delta t minus tau d tau, and the transformation is in the time index t. So since this delta t gives ht, then by time invariance property delta t minus t naught t will give me h of t minus capital T. So we'll get h of t minus tau d tau. So the convolution integral looks like y of t is the integral over minus infinity to infinity x of t h of t minus tau d tau. This is the convolution integral. Okay, so now let's look at an example, very simple example of this integral. So you have two pulses. One pulse is x1 of t and another pulse is x2 of t, which lies between, say, let's say this is t1 and this is t2, and I assume that t2 is lesser than t1. Okay, so one fits in the other. Fine. So what will be my yt then? Yt is integral minus infinity to infinity x of x1 of tau x2 of t minus tau d tau. Now we need to shift everything to the tau variable. Okay, so this is tau 0 to t1. This is my x1 of tau, and what is x2 of t minus tau? So look at this, from 0 to t2, this is my x2 of tau. Let me shift it to the right by t units. x2 of t plus tau means shifting to the left by t units, so minus t, and this is t2 minus t, so x2 of t minus tau will flip it, so this goes over here, becomes t, this goes over here, becomes minus t2 minus t. Okay, and now the variable here, or the, I should rather say, the parameter to change is small t. Okay, so let us look at various cases where this, depending on t, small t, my x2t's location will change. So this is one possible case where x2t can be present, where it does not overlap with my pink rectangle. This is the case 1. Then this is case 2, where it partially overlaps. Okay, see, there is no overlap here, there is some partial overlap with the left edge of the triangle. Then we have this region inside the rectangle where x2 of t completely lies full overlap within the rectangle. Then once you move this out, okay, so at this rectangle to the extreme left minus infinity, I slowly and gradually try to move this x2 of t into the x1 of tau. Okay, so this should be x2 of t minus tau actually. So this should be x2 of t minus tau. x2 of t minus tau, x2 of t minus tau, x2 of t minus tau. Then in this case here it's again partial overlap when it's trying to move out of this rectangle, and here you are out, completely out of this rectangle. So there are 5 cases. So here you once again have the case of partial overlap, 1, overlap 2, and here this is a no overlap 2. Where does this no overlap take place, or when does this no overlap take place? No overlap takes place when up to the location anywhere from minus infinity till this point. Okay, and what is this? This is the edge is t, so t can go from minus infinity till 0. So 0 minus infinity till 0 is my no overlap 1 zone. Then where is the partial overlap zone? So partial overlap starts from t equal to 0, that is here it just starts partial overlap, and here it ends partial overlap. How does it end? So this is what? Minus of t2 minus t is 0. What does it mean? This means t is t2. So from 0 till t less than t2, it's partial overlap 1. And then when do you have the full overlap? full overlap starts from t equals to t2 till t equals to t1. So t2 till t1, this is full overlap okay. And once again, from where will I have the second partial overlap? So it will start from t equal to t1 and it will end at here, t equal to t1 plus capital T2, okay, because this is t1 and this width is t2. So t1 till t1 plus t2 is again partial overlap 2, and beyond t1 plus t2 till infinity, this is the no overlap zone, part 2. So why have we evaluated this? We have evaluated this so that we can, because the product depends on the overlap, okay. So let's see, for minus infinity till t less than 0, x1 of t and x2 of, sorry, it should be x1 of tau and x2 of t minus tau, this is 0. This is 0. Why? Because there is no overlap. These are multiplied and they are and they won't meet each other, so their product is 0. The integral from minus infinity till any t, okay, and that is with 0, so it will give you 0. So y of t is actually 0 for this region. Now let's look into the second zone. The zone starts from 0 to t2, and what is that? In that case, x1 of tau and x2 of t minus tau, this is 1 and this is also 1, so it is 1. And where do you integrate it from? We won't integrate from minus, it will integrate, will start from 0 and it will end at t, okay, and this t will lie between 0 and capital T2. So it is 1, it will be integration over tau, so tau t t, so y of t equals to t for this interval, okay. And now we look into this for t2 less than t less than t1, x1 tau into x2 t minus tau, what is this? This is also 0, this is also 1, this is also 1, so the product is 1. And where will the integration limit start from? So once we are inside over here, let's say this is t is anywhere between t2, anywhere between t2 and t1, and it's completely inside, so this one will be t2 minus t, alright, minus of t2 minus t, or this is t minus t2, this is t minus t2, okay. So it will start with t minus t2 and it will end at t, and the product is 1, so you get tau t minus t2, so yt is capital T2 for the entire time between t2 to t1. I think I should have done the red color, okay. Now when it again starts escaping, the product is still 1 because you multiply into 2, and we are looking into the region of overlap. What is the region of overlap? It starts from t minus t2 and nz t1. Okay, any rectangle that I'm passing, so I'm shifting this, so this will be t minus t2 because it's variable, and this is a fixed region, it is t1. So it will start from t minus t2 because t eventually reaches a maximum limit of t1, so that it gets fixed. So 1 d tau t1 minus t minus t2 comes t1 plus t2 minus t. So it becomes t1 plus t2 minus t, and finally for the final interval t1 plus t less than infinity, this overlap becomes 0. Why? It's outside. Alright, so x1 of t to x2 of t minus tau is 0. So the integral starts from t1 plus t2. Sorry, we don't have any bounds, so we can say it starts at t minus t2 and ends at t 0 d tau, and that's 0. So it is 0 over here. So finally what we have done is a true convolution. I have shown you how to convert two rectangular pulses over here of different widths. Now let's look at the result and what is actually happening over there. I am fixing one pulse, making the, and fixing means I keep this x1 of tau constant because I want to evaluate y at every small t. So what I will be doing, I will fix one and then I will take this and I will first shift because I need x2 of t minus tau and I will be playing in the tau interval. So I take this, I shift it to left by small t and then I flip it. I will take this pulse, flipped pulse actually, and then based on the value of small t I'll move it left or right. Okay, so I start from t which is at minus infinity, so it's all over here, and slowly this t comes in. Okay, and at each and every t I evaluate this integral over here. Okay, so we won't be actually evaluating the integral, we'll make use of smart sense because all over from 0 to minus infinity there is no overlap between this small pulse and this big pulse, so the product becomes 0 and ultimately our output becomes 0. So that's why what you have seen over there is that I have classified this region into 5 zones, each of them giving different characteristic. Starting edge and the ending edge of this is different, so it's like a sliding window. Okay, I'm sliding the window and the window has some overlap with the other window which is fixed. So what does my yt look like? Yt is 0 t t2 t1 plus t2 minus t and 0, and for what intervals? Minus infinity till 0 is from t till t2, from t2 till t1 plus t2, and is from t1 plus this one is till t1, this one is from t1 till t1 plus t2, and this one is from t1 plus t2 till infinity. Okay, so now let's finally start drawing it. So initially the overlap portion is all in red 0, then we start rising until we reach small t. Once we reach capital T we become stable. By stable I rather actually mean to say that it becomes constant, and again it drops down and it becomes 0. This is what this is the result of our convolution. So the convolution of two this one is t2, this one is t1, this one is 0, this is t1 plus t2, and this one is t2. Okay, so this is the generic trapezium that you will get when you convolve two pulses of unequal length. Okay, and this region is determined, this length is determined by the shorter pulse. Okay, now let's look into a question that was provided to us in the assignments. So it was given that xt is 2 for 0 2, otherwise it's 0, and ht is x of alpha t. So what we need to do, we need to determine yt, which is x of t convolved with h of t. All right, so how do we go about it? We shall make use of the result that we have learned over here. xt is 2 from 0 till 2. H of t is and it's given that alpha is greater than 1. So what will be h of t? H of t will be something like this. Why? Because we are scaling it. We are scaling it when you are scaling it as alpha t, when alpha is greater than 1, then your pulse will shrink down. This is 2. So what will happen when I convolve them? Okay, so at first we will ignore these 2's and just look into it. So in this case, as you can see, t1 is 2 and t2 is 2 upon alpha. Okay, so how will our pulse look like, trapezium look like? It will start at 0 and then go up to 2 upon alpha, and then it will stay over there. After some time it will return back at 2, and this will go down at 2 plus 2 upon alpha and stay at 0. And this is what? This is 2 upon alpha. Okay, but look over here. These pulses were assumed to have these pulses were assumed to have these values of 1. Okay, amplitude 1. Here what is happening? Here we have 2, here we have 2. So 2 times 2, that's 4. So what will happen is that this amplitude will simply get magnified by 4 and it will become 8. So it was 4 times 2 into alpha, it was 8 alpha, because t2 is 2 upon alpha, to 4 times t2 is 8 upon alpha. Fine. Now how do we write this in terms of the ramp function? Remember our ramp function that I had mentioned in the previous lecture? So it's a unitary function, it's a typical function rt, which is 0 when t is less than 0, and it is t, it is a slope 1 when t is greater than 0. Okay, so what are the slopes over here? Initially the slope is 0 over here, so you don't have anything to worry about. We suddenly have a rising edge. We have a rising edge, and what is the slope of this rising edge? The slope is 8 upon alpha by 2 upon alpha, that's 4. And where is it originating? It's originating at 0. So what will we write? 4 times r of t. 4, this is the slope. Slope is 4 times and it originates at 0. So r of t minus 0. Now it was supposed to go on like this, but now it has moved down, so there is a slope change of -4. Okay, so this was +4 slope, so there is a change of -4, so we'll write -4, and that's a ramp, and because it is a ramp, it will keep on moving forward. So write 4 ramp, and where has this ramp been created? This negative ramp has been created at 2 upon alpha. So 4 ramp 2 minus alpha. Then again, if you see, I was supposed to go on like this and this being a ramp, but now you see this is going downwards once again. Okay, so this is a further downgradation by 4 units. You see, this is also actually 2 alpha, and this is this 8 alpha, so the slope is still 4, -4 actually, so it will be -4. And where did this ramp take place? At 2. So -4 ramp 2. So as just like the previous cases, I was supposed to be moving downwards like this, but then I am moving like this. That means there has been an improvement of the slope. By how much? By 4 units. So I will write 4 times ramp t, and where did this ramp take place? 2 plus 2 upon alpha, so -2 plus 2 upon alpha. So if I simplify it, what do I get? I get 4 times ramp of t minus ramp of t minus 2 upon alpha minus ramp of t minus 2 plus ramp of t minus 2 plus 2 upon alpha. Alright, so this is the final expression for our trapezium. Okay, now the question that follows after this is, for the above yt, what value of alpha yields 3, or what value of alpha causes 3 discontinuities in the derivative dy dt. Okay, now let's look at it carefully. Okay, it starts at 0. Okay, so I'm getting straight lines now. Very good. Okay, very good. So 2 upon alpha, 2 plus 2 upon alpha. What discontinuities, or what will dy dt look like? So okay, sorry, this shouldn't be dy dt. This is yt. So how will dy dt look like? This has a slope 0. This has a slope 4. This has a slope 0. This has a slope -4, and this has a slope 0. So it will be all in terms of unit step. You can write this also as a function of ut. So it is 0. From 0 onwards you get 4 over here. At 2 alpha this drops to 0. At 2 it again goes to -4. Here it becomes 2 plus 2 upon alpha. So how many discontinuities are there in this function? You have one discontinuity over here, you have a second discontinuity over here, you have a third discontinuity over here, and you have a fourth discontinuity over here. All right, when can we have 3 discontinuities? Look at it very carefully. we will have three discontinuities when the second and the third discontinuity meet. Why? Because I am taking alpha as a parameter. When I take alpha as a parameter, then these widths will change. 0 will remain fixed, 2 upon alpha will change, 2 will remain fixed, this will change. So what do I need to do? I need to choose an alpha such that this edge meets at 2. So what do I need to do? 2 upon alpha is equal to, and then alpha equals to 1. It's very simple, but you will be able to reach this answer only when you are able to get the previous answer correct. So it's always good to ensure that your answers are to recheck your answers. Otherwise, subsequent there are certain questions where you have to use your previous answer to decide the next one. All right. Okay, so now we move on to the next topic, which is the commutative, distributive, and associative. So what does the commutative law suggest, or what is the commutative property? So we know in addition that a plus b equals b plus a, or a into b equals, I should write here multiplication over here, b into a. This holds for any operation to be commutative. These properties, let's say we define a new operation that is applicable on two operands a and b. Commutative means that a delta, or that operation into a b, will be same as b delta a. For example, okay, this let's say this delta a delta b, let's suppose it means 2a plus b. Okay, fine. This delta means an operation which I am defining as 2a plus b. So what will b delta a be? B delta a will be 2b plus a, because the order is mattering over here. Who is placed where, that is very important. Okay, so what does it mean? It means a delta b isn't equal to b delta a, and this implies that delta is not commutative. This is just a brief outlook into the commutative property. I am not, and this is a part of hardcore algebra. I am not going into that any further. So in terms of linear systems, what do we mean by commutativity? When you have two xt and you get an output yt. What is yt? Yt is xt convolved with h of t. What is that? Integral minus infinity to infinity x of tau h of t minus tau d tau. And you can easily show by change of variables that this is the same as x of t minus tau h of tau d tau, and that's h of t convolved with xt. So the filtering or the convolution is a commutative operation for linear time invariant systems. So what can we do? If we have a signal which is h of t and we pass it through a system whose impulse response is x of t, Let's suppose I have this x of t as a triangle and this h of t of the system is square. Okay, I am defining it as signal, and these signals by these names xt and ht. I am not meaning xt and by an ht as impulse response and this input signal anymore. I am changing the definitions now for now. And now what happens? Let's suppose I apply the input h of t. That means I apply the input to a system whose impulse response is a triangle. I'll get some kind of a paraboloid, some output yt. In both these cases, my output will be the same. Okay, so whether I give a triangular input to a system whose impulse response is a square or vice versa, that means I give a square input to a system whose impulse response is a triangular shape, both the outputs of the system will be the same. Then this is the commutativity. This is mathematical nature, not, I can't give too much of a physical explanation to it. Then we have the associative property. What does that associative property mean? For example, addition a plus b plus c is same as a plus b then c. That means first you do operation on b and c and then do it on this. It is the same as first doing on a and b and then doing at c. Same goes with multiplication. A times b into c is same as a times b times c. That means first you multiply b c, then you multiply it with a. This is the same as multiplying a with b and then doing it with the c. And let's look at this delta. This delta a delta b then delta c. What is this? 2a plus b delta c. And what will this be? 2 into 2a plus b times c. That's 4a plus 2b plus c. And let's look at this other case, a plus delta b plus c. Sorry, a delta b delta c. That's 2a. No. We work on a delta 2b plus delta plus c. And what will this be? 2a plus 2b plus c. So you see both of them are different. So clearly delta is not associative. So what does this mean? xt going into h1. Yeah, Ankit Kumar, you seem to have a question, so you can switch on your microphone.
Sir, I want to know about operator delta.
Okay, means
Can
what is
you?
this? I have defined this by myself. I mean, by delta, what I mean to say is that the associative properties in generally for any addition multiplication. So I wanted to take an example to show what an operation means. Okay, so just like addition, multiplication, division, subtraction, or this convolution. So I have defined this delta operator myself as an example to show you cases where associativity or commutativity do not hold. Okay, so this delta I have defined it on my own. You can define your own operations. Oh, is that clear?
Yes.
Thanks. So, oh sorry. So you have xt, then you have the first block h1t, then the second block h2t. So what is the output? The output, if you look physically, xt is being operated upon by this system h1t, which will give me an output y1t. Now this y1t is going as an input and is being operated upon this with this h2 of t. So what can I write? yt as h2 convolved with like this. Alright, now let's look at the other case. xt h2t h1t yt. So what is this? Oops, this should be x. So what can you look at over here? h1 convolved with h2 convolved with x. Okay, so here I have exploited, if you look very carefully, I have exploited commutativity also over here. So you can also say directly that h2t goes into x of t goes into h1 of t gives me yt. So it's all the same, so all of them are the same. So what actually physically what we would like to show is that even if you interchange the two blocks, the output will still be the same. Okay, and this often helps in simplification whenever you're dealing with block diagrams, because this is the associativity, and then you have the distributive property. It's a bit different, it requires two operations to perform upon, so I will directly jump into the convolution stuff. Okay, so let's say you have a system h1 convolved with h1. Okay, so let me state it first and then I will draw the diagram. h1 plus h2 convolved with h3 is the same as h1 convolved with h3 plus h2 convolved with h3. So how will it look like? You have h1 of t, this box and this box, they add, and this goes into h3 of t. It's the same as bringing this box inside. h1 convolved with h3 and h2 convolved with h3. Alright, this is simply the distributive property, just like our normal multiplication and addition. Okay, so we discussed the distributive properties. Now we shall look into memorylessness, invertibility, causality and stability. Okay, so often you will encounter questions where you are given a description of a system, you are given some mathematical relationship between the input and the output, and based on the relationship you are supposed to determine the properties of the system, whether it's linear or time invariant, with linear or non-linear, time invariance. These two steps were explained in the previous lecture, and then in this one we will talk about memorylessness. Okay, so the memory property. So what does this mean? If yt depends only and only on x of t, that is a function of xt only, like what are the examples? Yt is sine of xt, yt is x square of t plus 3, yt is 1 plus 1 upon exponential of minus x cube of t, In all these cases you are using only x of t. That means the value at t depends only on the output at time instant t, only depends on the input at the same time instant. This means the memoryless property. Okay, and this is the memoryless property. If yt, if you see, it's a function of, let's say, x of t comma x of t minus past, or x of t plus future. Okay, so this suggests that this system has memory. For example, yt is x of t minus 2, yt is x of log of 1 plus t. You are working with time, you are harassing time over here. I mean, by harassing I mean that you are using future values, you are using future memory. Or yt is x square of t plus 1 upon x of t minus 3. You are using past values. And for an LTI system which is memoryless, it's possible only for yt is equal to k into x of t. Okay, there is no other system which can be LTI system which can be memoryless apart from this. So what is the corresponding impulse response? It's simply k delta t, a scaled version of the Dirac delta function at the origin. It can't be anywhere else, otherwise that will suggest a delay, a memory. So it's very easy to identify systems with or without memory just by looking at the form. Now let's look at invertibility. Let's say you have a system, you give the input to the system xt, the system is ht, and you get the output yt. Now you create, or you get another system h hat t, such that the output to your system is xt. So in such a case, this is called the inverse of the system, and it is not necessary for all systems to have inverses. Not all systems have their inverses, and in general some cases the inverse is difficult or almost impossible to realize. For example, let's say if you have a system T1 which satisfies this relationship, yt equals x square of t. Okay, so you look at it. If I give xt equals to 2, or I give xt equals minus 2 to T1, then the output will always be 4. Now if I have 4 only, then there's no way for me to determine back whether it came from a 2 or whether it came from a minus 2, because I lost that sign information in the squaring operation. Alright, so this system does not have any inverse, no inverse. If you think that it will be square root xt, let me tell you, it will always give me a 2. Square root of any positive square root of any, let's say, a square, will give me a positive number only. So square root is never the inverse of x of t. If you know that xt is always positive, then you can say that yes, under the condition that xt is positive, then you can say that yeah, this inverse is actually valid. Now let's look at yt as x of t upon 5. So what can our inverse be? You're dividing by 5, multiply by 5, easy, this is the inverse. So there is no generic way for finding inverse. Some of them may be straightforward, some of them are very indirect. So you should use some of the rules which you had learned in let's say class 12 to find inverse of functions. Okay, like what we often do is that if we have y equal to f of x, then what we do is try to write x equal to f of y, writing this form, and then we get something of y equals to gx. Okay, what I am saying is that we have a function y equal to f of x, replace y by x and x by y, and try to write y as a function of x, and that g will be some other function. This g is the inverse of f. Okay, now let's look into causality. So systems can be causal, non-causal, and anti-causal. When is a system anti-causal? When is a system causal? A system is causal when yt depends on xt and or x of t minus k, where k is positive value, that means present or the past. When can you say that if you it's causal? When you see that yt depends on xt and or x of t minus k and x of t plus k1 k hat, both k and k hat are greater than 0. That means either present is there or past is there. Either of them has to there has to be a past term or at least a present term, and there's a future term also. Okay, future term is there and the past term has to be there. Okay, past and future, both of them have to be there, then it's non-causal. And when yt depends only on x of t plus k hat, when it only depends on future, then we say that the system is anti-causal. And for linear time invariant systems, LTI systems, how do you determine? If ht is anything, ht is 0 for t less than 0, then it's causal. If you see anything like this or anything like this, that means ht not equal to 0 for t greater than 0 or t less than 0, at least for finite or infinite interval, then this is non-causal. That means it should exist both side, and it can be either finite or infinite duration. That means that you could have something like this or something like this as well. I am talking about the impulse response. And now finally, just hold on a second. Yeah, recording takes place. And finally, the case, if you see, this is one case, this is one case, and the final case was anti-causal. And when is it anti-causal? Whenever this side is never used. For example, here this side is never used. ht equals to 0 for t greater than 0. This is anti-causal. And let me tell you, anti-causal systems are time machines. Anti-causal systems, non-causal systems can also be considered as time machines, but anti-causal systems are completely take you to the future. They won't take you to the past. Okay, so in one or the other way, you can say that anti-causal systems never exist. Even non-causal systems cannot exist because they can take you to future as well, both past and future. But causal systems can exist. Okay, this is causality. And finally, we have stability. Stability. So whenever you look at the impulse response, okay, so there are two ways in which you can look at stability. If you have some relation yt between yt and xt, that is the input and output, or its past or future functions, what do? You assume that the xt, the signal, can take a maximum value of m or a minimum value of minus m. That means your signal will always be bounded by a finite value m. Okay, that means it is lower bounded by minus m and upper bounded by m. Okay, xt. Now try to check the yt upper bound and lower bound. If both the bounds or either of the bounds are infinity, then your system is unstable. So if mod yt is bounded by some bigger interval or smaller interval b, and if b is less than 0 and you determine b, then you say that the system is bounded or stable. If you see that it's not getting bounded, you get something like dependent as a function of time. Okay, so you can get to see that yt is something less than equal to t. That means that as your time will progress, your yt will can keep on growing. It can go up to infinity if you let the system respond to the input. You are giving us input which is bounded between minus m and plus m, but your output keeps on increasing as time progresses. So this is clearly an unstable system. Okay, so you give a bounded input and you should get a bounded output. So we call that Bibo stability. Bounded input, bounded output. This can be used to check the stability of general systems. And for LTI systems, what do we do? LTI, we have the h of t. So at the end of the day, if you apply bounded BIBO stable condition in LTI system, you will be able to see that the area under the absolute value of the h of t should be less than infinity. That means the area under this curve impulse response must be finite. Okay, so this is stability. So I'll just show you a few examples and we'll complete today's session. So let's look at a system. H of t is e to the minus 9 mod t. So you have to determine the kinds of systems. Okay, it's LTI for sure, because it's only when the system is LTI we'll be able to calculate its impulse response. No, impulse response can be calculated, but it can be used in convolution. Linear time invariance can be applied. You are using it in convolution integrals. So LTI is for sure linear and time invariant. Now let's look at memory. You see over here, for memoryless system, we were supposed to have a k delta t kind of a impulse response. But here, since you have a convolution integral, This integral will give you past and will depend on past and future values of x of t, right? So this has memory. Inverse, it would be okay if we don't talk about it now. We may talk about it later when we discuss, or even if we look at it, h of omega, we know e to the power 1 mod 80 2a omega square plus 9 square, 9 is 18 omega square plus 81. So inverse, if we actually look at inverse system, h inverse of omega would actually be 1 upon h omega. And let me tell you an important property. If you have two signals xt convolved yt, their corresponding thing in the Fourier transform is the product. Okay, so convolution in time domain becomes product in the frequency domain. Okay, so all this thing, if we know you can calculate its Fourier transform easily. You can also calculate its Fourier transform easily. So now if I ask you to calculate the Fourier transform of this, you don't need to do all that math, because there is a t term and all that. You very difficult to do those integrals. You can simply take this sinc t and this sinc t upon t1 and this sinc t upon t2 and some other constant terms will be there, and you multiply them. Sinc omega, actually it should be sinc omega omega 1 sinc omega omega 2. So it will be product of two sincs, sinc omega 1 times sinc omega 2. That's it. Very simple. All right. So there's memory. Inverse, we have the inverse, but there are certain conditions where for the this omega square plus 81, this actually gives an unstable system actually. So the inverse of the system, I'm not stating it further, we won't deal with it, but then the inverse of this system is actually unstable. So although if we are able to find a system also, but then the corresponding impulse response is infinite. Now let's look at causality. It's two-sided, it exists here and here as well, so it's non-causal. And look at stability. We can evaluate e to the power minus 9 mod t dt. Okay, so see, this is exponential is finite area, so this is less than infinity, so this is a stable system. Okay, so we found that this has memory, this has causal, this is a non-causal system, and this is a stable system. Okay, now let's look at a different system, ht e to the power minus t plus exponential of t minus 5 upon 2 ut. Does this system have memory? Yes, because it's not of the form delta t. Let's look at its causality. Look at two terms. It's an e to the power minus t. There's no ut or u minus t. It exists everywhere. Okay, and this one is an exponential which starts at u0, so it will have some kind of a discontinuity, but it exists for negative and positive values. So this is non-causal. And you look at this, there's this e minus t. Integration of e minus t dt will give me infinity. So this is an unstable system. All right, so let's look at another system. ht is e to the power minus t cosine 2t ut. So how will it look like? It will look something like this ht. This system, it's not of the form delta t, it has memory. Causality, it exists only for t greater than 0, it's 0 for t less than that, so it's a causal system. And if I look at stability, it's a damped exponential. If you took that exponential, you would have already got some finite value. Now you are multiplying by cos. The cos actually is less than or equal to 1. So this integral will also be some finite value. You will be able to calculate this integral, but you don't need to. Just need to check whether this integral is finite or not. That's it. Because e to the power minus 2t mod t cos t is always less than e to the power minus 2t, and this integral is finite. So it's obvious that this integral has to be finite. So that means our integral is finite, and this makes our system stable. Okay, so that's it for today. And yeah, one more important property, that convolution in time domain leads to multiplication, scaled multiplication in frequency domain. So it's always better to go to frequency domain or the other domains that we'll be learning in the upcoming weeks. We rather than doing this convolution, which is a very lengthy thing, we go for the multiplication kind of operation in the other domains. Okay, so I hope everything is clear. If you have any doubts, please let me know. Otherwise, I will close this session.
Sir, I have a doubt.
Yeah, please.
Not for today's session. I have a doubt regarding entire signal system course.
Sure.
In future, I am a BTech in final year. I have undergo this course in previous semesters in my college.
Yeah.
What are the future scopes in the signal system?
Okay, let me tell you. This if you're talking about pure signals and system course, so this is a very fundamental course. It can lead you to this irrespective of whatever stream you go in, pure electrical or electronics and communication. Whether you go for circuit analog circuits, except the semiconductor stuff, pure semiconductor stuff I'm talking about by device and material physics. Apart from that, if you go into analog circuits, you will require signal systems. If you go into digital circuits, you will require signal systems. If you go into communication systems, you will require signals and systems. If I count each and everything requires signals and systems. Is fundamental. Okay, that's one thing. But now tell me, are you especially talking about signals and systems or signal processing?
I have undergo a course digital signal processing, and I have learned few methods in that.
Okay.
But I don't have so much idea of this.
Okay. So since you're in final year, I'm sure you must have appeared for GATE, right? So
Yes.
did you appear for GATE?
I appeared, but I don't have a good score.
Okay, sure, no problem.
I'm
Yeah, please continue.
I'm just near boundary. I just qualified.
Okay.
That's
So maybe he will be repeating, or then and repeating in the sense that you will be taking some course on preparing for GATE next year, right? So yeah. So talking about signals and processing, there are multiple avenues if you are thinking of higher studies, right, in the IITs or IISc. Okay, so we have a separate specialization called in the signal processing. Now depending on the some IITs don't have this specialization directly, especially IIT Kharagpur, IIT Bombay, they don't have something called signal processing. The reason being that what I told you in the just a few moments back, that signal systems is so fundamental that you require in all the branches, that you can do it in circuit systems, everything. So signal processing will be helpful if you want to look into a career towards it. That will be good. So first I would say that you try to appear for the GATE for the next year and improve your chances, and maybe you can join the signal processing courses of any of the IITs. And future scope is always bright, because signal processing is always associated with every electronics is essentially signal processing in one way or the other. So if you look into circuit side, so you can join into the VLSI, but then some people lose the signal processing aspect of that. But that's signal processing in another sense, because generally you're learning how to design systems to deal with the analog or the digital systems. You're more into the circuits part. So that's one side. You can do the VLSI side, but you need to make the circuits. That training you'll get in MTech. But first and foremost, I will say that you try to focus on your gate and make the fundamentals clear. Once you clear that up, then you can join into either the signal processing branches or the circuit branches.
Sir, one more thing I would like to ask.
Yeah,
The certificate of this course, NPTEL course,
yeah.
uh, where I can use. Is there any sector that is not known to me?
The basic, if you are trying to use this for certificate for the pure signals and systems, I don't know whether it would be too useful, because I doubt it's you practice use utility of this certificate of this course. I mean, if you're talking about these signal systems, I doubt its practicality of being used in any interview or anything, because this is a core course which every engineer undergoes in his undergrad. So it's a quite obvious thing. So if you have had any course like deep learning or machine learning, which is not a part of a core course, then that helps when you're applying for interviews either in MTech or more. Other than that, is more it helps more in the interviews in the jobs. But since this is a core course, then it won't help unless you are doing these for your college course credit completion. Often colleges have course credit requirements, so that credit requirements is fulfilled when you do such courses. Or if you are since you are a student, but for faculties of other colleges, they often have some FDP, faculty development program requirements, so they also use that over here. But for your case, I frankly I should stay unbiased. But then if you ask me personally, pure signals and systems course wouldn't make much of a difference anywhere, because it's anyways there in your semester.
Yes, sir. Thank you, sir.
Okay, so any other doubts, any other suggestions you would like to know? Because I can tell you that there are a lot of there are ample jobs there in the industry out for signal processing.
I have come to a few websites. Uh, they give information about jobs in PSUs and different central government institutions
Yeah,
and companies.
yeah.
Uh, will
Your voice is breaking.
believe that are there
Your voice is breaking. Hello.
am I audible?
Yeah, you're audible now. Yeah,
Uh,
you're audible. You can
I
continue.
have yes. Uh, I have got information about different openings in government companies of central government.
Yeah.
Are there any other opportunities? We leave that.
Mm, Opportunities in the sense of what? You're talking about signal processing, or in general from gate perspective? What do you means? Whose
I am
applicability you want
in
to know
general.
for this? Means gate for government exam or signal processing for government exam?
No, no, I am talking in general, yeah, without a signal processing. I'm in undergrad final year.
Okay, so you want to know how will gate help you? Is that so?
No, not. I have. Gate helps me. I think Gate helps me in admissions in IITs and institutions and jobs in PSUs.
Yes, yes. So what do you exactly want to know? Your doubt is not clear.
I want to know: are there opportunities with the other? Are there other opportunities?
Yeah, there are other opportunities, but in the private organizations. So you can apply through online job portals such as LinkedIn. But if you ask me, unless you come from really, let me stop the recording. That would, yeah.